Welcome back, guys. Now we are going to discuss on the margin bounds. In addition to the generalization bound, Vapnik uh, also studied and just came up with what is referred to margin bound. The margin bound is basically defined in terms of the distance we have in between a sample of positive, so to speak, elements and negative elements. The greater is the difference in terms of distance from the closest element from the negative set to the closest from the positive set. The greater it is, the smaller is the shattering coefficient. So if the shattering coefficient is smaller, of course, our empirical risk minimization principle is going to converge for a smaller sample size. So we say it's going to converge faster to zero. And this is quite interesting, and that's the origin for the support vector machines. So when we talk about support vector machines, we are especially talking about the margin bound. So just to have like a big picture, Vapnik proved the Vapnik-Chervonex dimension for a given space of admissible functions to be smaller than or equal to D, which is the input space dimension. Okay, so this is the number of dimensions we have in our input space. For example, 3 or 4 or 5, that depends on the number of variables we have. For example, if we consider the iris data set, we've got four attributes. So our D is going to be 4. Okay, so it's a minimum in between that dimension and 4 times the smallest as possible open ball enclosing all elements we have in our space, powered to 2 divided by some rho powered to 2, in which this P or rho represents the margin, represents exactly the distance from this hyperplane to this support hyperplane that connects the closest points from the positive class, which is the same distance, of course, from this hyperplane for this other hyperplane, support hyperplane that touches the negative points on the other side. So rho is exactly this distance over here, which is the margin. Okay, so this distance overall is like 2 times the margin, twice the margin. Okay, plus 1. With this formulation, it turns out to be easy to observe that maybe our space has, for example, 100 dimensions. And let's suppose my R is like equals to 1, and my rho over here, or P if you prefer, is going to be very close to 1 as well. That's the same as having like a bunch of points over here, a bunch of points from the other class over there, and this margin turns out to be almost the same as this radius enclosing all points in our space all together. Okay, just to give a practical idea, let's see over here. I suppose we've got, I can go back, I think it's easier. R, this term R, is going to be the distance we have from a central point. This is the whole data set. So consider the central point is like in here, and it is the smallest radius that encloses the whole data set. So it's like, given this central point, let's say the smallest radius goes up to here, and then that is enough to enclose all points together. That's our R. That's this term here, R. And rho, as I mentioned before, that's the margin, which is the distance, the Euclidean distance from this hyperplane to this support hyperplane. This is the hyperplane that classifies our sample in positive and negative, and this support hyperplane is like the sidewalks we've got in a given road or in a given street, just to define where it starts being positive, from which point starts being positive, and from which point starts being negative. And of course, the road or the street is in between those sidewalks. Okay, just to have an idea. I'm not going to go into the details on this Vapnik-Chervonex dimension based on the margin bounds. I just want to motivate you guys to understand that based on the generalization bound, Vapnik came up with some other formulations, theoretical formulations to provide some additional guarantees, additional learning guarantees, of course, in this scenario. This is the formulation that came up after the generalization bound. This is the expected risk, as we mentioned before. This is the empirical risk. You observe that empirical risk here is represented by a new factor, a new Greek letter of f. It is the same in this context as the fraction of training samples that present a margin of at least equal to rho or p. That's the same as saying which are the elements that lie inside the margin. For example, here we have a sidewalk, which is a support hyperplane for the negative class and a support hyperplane for the positive class. Let's suppose that here we could have like a positive element which is inside the street, okay? And another negative here, which is also inside the street, and maybe another negative over here. How many examples we would have inside the margins? We'll have one negative, which is, by the way, on the wrong side, should be on this side, but it is on this side. Doesn't matter, but it's on the street, so to speak. And of course, a positive that's here and another negative that's here. Besides, they are on the right sides of the hyperplane that crosses over here. They are in some mixing region, a region that is defined from this support hyperplane up to this support hyperplane that should somehow be without points lying on it, just because it's like a mixing or a region that increases the uncertainty of belonging to the positive or the negative class, of course. So this nu of f over here is the fraction of points of training examples, or of course the fraction of points of my sample that lie inside that street. I mean, if I've got like those 3 points inside the street, my fraction of elements of input samples that lie somehow inside the margins would be like 3 over the total number of points we have in here. The total number of points. That would be like 3, which are here, and all the others, which are over there, okay? So this would be a fraction of how many instances or input examples we have some uncertainty on classifying, okay? That would be our fraction over here. And over here we have some c, which is a constant. Remember that the generalization bound used c equals to 4, and here we know we have some constant, okay, to be satisfied. N is the sample size, as you guys know. Here n is the sample size, and all this together is our Shattuck coefficient. So you guys can notice that the Shattuck coefficient reduces if this guy R, which is the smallest, the radius of the smallest open ball enclosing the whole data set, no matter the class, again, remember, no matter the class, all data points divided by the margin is really, really close to 1. If this is close to 1, I will have just log of n power to 2. But on the contrary, if my radius is very large, and of course, this hole is quite small, and tends to be really close to 0, this is going to increase a lot. By increasing this, again, all this together is the same as having some power, some n power to some constant p, as we discussed before. So that's the same as increasing the scattering coefficient if r is very large and rho is very small, as I mentioned before. Okay? The better is, of course, when this and this are quite similar, very close. That's the same as containing all points from the positive class in a single place over here, all positives, all negative points on the same region here. So my R, my radius enclosing everything, is going to be quite similar to my margin hole. And of course, this would reduce as much as possible my scattering coefficient. Just to have an idea, if I go back and open R over here, let's suppose I have like R equals to 1 power to 2 divided by some rho, and rho is almost 1 power to 2. Times this, of course, times my log of n powered to 2. Let's define my n from 1 to like 10,000 to be, and I will plot this so you guys can see my scattering coefficient, how it reacts, how my scattering coefficient reacts. Of course, if instead of that, let's suppose I have like 0.999 over here, and I plot it using some red line. So it's going to be smaller, even small, my scattering coefficient. But what happens if instead I decide to plot something in green that is like, let's say my hole over here is going to be 0.01 to the square. I cannot see it. It's over here. Take a look. It's going up. I better plot this in green beforehand so I can see it. And now I can plot, like using lines, I can plot in black, my first function, which would be 0.99 to the square. Take a look, it lies down here. So there's a huge difference in terms of scattering coefficients, as you guys can see, as you guys can notice, if my margin is very small. But if my margin is very small, is here, sorry guys. But if my margin is very, very large, almost as large as R, my scattering coefficient reduces a lot, as you might see over here, okay? This delta is the same delta we discussed before. It is the confidence level we wish to ensure for the uniform convergence of our empirical risk minimization principle, as you guys might remember, okay? So I can tell you, and finally, that the most important about this large margin bound is that it shows me that if I have a single hyperplane, this works for a single hyperplane cutting a space dividing the positive and negative classes, okay, in a given space. The greater the margin is, and of course, the closer it is to my radius enclosing all points in my space, the smaller is going to be my shattering coefficient, and the faster, and by faster I mean less training examples, and I will need to ensure the uniform convergence. This is the main motivation for the support vector machines. Actually, support vector machines are the best classification algorithm we have, but they are the best only and only if our space, our input space of variables allows to divide the space in a linear fashion, allows to separate, linearly separate like this, the positive from the negative elements. If I have like a bunch of points at the center and some other points around, I cannot divide, I cannot separate the positive from the negative elements with a single hyperplane. I need to come up with a linear, with a space transformation. And by space transformation, I mean I should transform the space using a kernel, and we are going to discuss kernels later, to come up with a different space like this, which makes possible to linearly separate or linearly divide the positive from the negative elements, and then classify my sample. Okay, and of course I expect it to work properly in the real world scenario. In order to ensure that, I should have a sample that grows at least up to a limit, and then I could test in this margin bound to understand how my expected risk is going to behave. So for instance, let's suppose we have, for sample size equals to 1000, we've got like 0.01 as the fraction of, or empirical risk, basically the fraction of training samples or samples or examples in my sample that present a margin of at least equals to p. Okay, and then let's suppose we plug all those elements here, we compute which is the R, or the ball enclosing the points, and which is rho for our instance, and we come up with this upper bound for our expected risk. And then we increase our sample, we increase it, and see what's going to happen with the expected risk. That's the same as doing something like this, as you guys might notice. Let's say our nu of f is going to be like 1%, okay, or 0.01. And let's suppose our n is going to assume values from 1 to, I don't know, it would be like 1000. And let's say our r starts with a given value. Let's say it starts somehow with a value like 0.9 and goes up to 1, and it stabilizes around 1 after, let's say, like n equals 1000. Okay, and our whole happens to be some value around 0.1. Here I'm going to produce something like a normal distribution, just to, no, normal distribution is not fair, something more stable. Could be like starting with, I don't know, 0.1 and going to up to 0.2 after stabilizing around 1000 elements. Okay, then I plot our v of f, or nu of f, Greek letter, the square root of some constant. Here I'm going to define my constant as 1 just to start with. Doesn't matter much because my n is going to go up. That's the problem. That's the question over here. And here we have my r to the square divided by a whole to the square times log of n powered to 2 plus log of 1 over delta, and I'm going to use the same delta used before, which is 0.05. So I want to ensure I have a good estimation for 95% of the cases, as we've seen before. I'll have like some values over here, and I'll plot those for you. You guys can notice we are converging, but we are far from having like a value smaller than 1, as you guys might see here. So I'm going to increase my sample size. Maybe I could increase to 10,000. Okay. Of course, I need to produce my whole again and my R again to 10,000. Okay. And then I'm going to use the same nu of f, which is 1%. And then I will plot this once more. Let me see what happens. It is converging. Of course, now it's smaller than 1. I can plot this in the y limit from 0 to 1. And you guys can see after 10,000 observations in this particular scenario, we have some expected risk, that is below something like 0.4 to 0.4 something. 0.4 is not good enough, so I'm going to increase my sample size in another order of magnitude. So I'm going to increase again my series of observed margins and my series of observed radius, open ball radius enclosing all the data set. Okay, and then I will plot it once more, and now I expect to have a nice convergence. At this point, my expected risk is below 0.2, below like 20%, okay, of risk. Of course, if you need a stronger, a tighter bound, I mean a smaller expected risk, I need to increase my sample size. I need more elements to train with. And that's what I'm trying to illustrate by increasing my sample size like this. I'm just trying to illustrate that. We're going to tackle that kind of problem, of course. Plotting, we're going to see that now we are even closer to 0. We are closer to 0 over here. Sorry about the noise over here, guys. But we are like below 0.1, which looks like 10% of expected risk. Of course, I can increase even more my sample size. Okay, that's all in this class. Now we go for the next, in which I expect to discuss more on the shattering coefficient. See you guys.